Capacitance and dielectrics. In this session, we will explore the fundamental concept of capacitance, beginning with an understanding of what a capacitor is and how it functions as a circuit element. We will define the two conductors that make up a capacitor, often referred to as its plates, and establish the mathematical definition of capacitance, denoted by the symbol C. From there, we will discuss the SI unit used to measure this property, the farad, and look at a specific physical example involving the capacitance of an isolated sphere. By the end of this section, you should have a clear grasp of how these components store electric charge and the geometric factors that influence their capacity to do so. Capacitors are incredibly versatile components found in a wide range of modern electronics. You will find them in radio receivers where they help tune into specific frequencies, or in power supplies where they act as filters to smooth out electrical signals. They are also vital for rapid energy release, such as in cardiac defibrillators, and play a role in the tiny accelerometers inside your smartphone that detect orientation. To understand how they work, think of a simple analogy. Just as a milk carton has a specific volume capacity for liquid, or an object has a heat capacity for storing thermal energy per degree of temperature, a capacitor has a capacitance. This represents the amount of electric charge the device can store for every unit of potential difference applied across it. Structurally, a capacitor is defined as any combination of two separated conductors, which we call plates. The illustration here shows two arbitrarily shaped conductors. When the capacitor is charged, these plates carry charges of equal magnitude, Q, but with opposite sign, one becomes positive while the other becomes negative. This separation of charge creates an electric field between them, represented by the orange field lines. Because of this charge distribution, a potential difference, V, is established between the two conductors. Even though the net charge of the entire system is zero, when we talk about the charge on a capacitor, we are referring to the magnitude Q on either one of the plates. Experiments demonstrate a direct relationship between charge and voltage. The charge Q is linearly proportional to the potential difference, V. The proportionality constant in this relationship is what we call capacitance. Mathematically, capacitance C is defined as the ratio of the magnitude of the charge on either conductor to the magnitude of the potential difference between them, expressed by the formula C equals Q divided by V. It is important to remember that capacitance is always a positive quantity by definition. When using this equation, we treat both the charge and the potential difference as positive values. While the charge and voltage can change, the capacitance itself remains constant for a given capacitor, because it depends primarily on the shape and the physical separation of the conductors. The standard SI unit for capacitance is the farad, abbreviated with a capital F, named in honor of the physicist Michael Faraday. 1 farad is defined as 1 coulomb per volt. In practical applications, the farad is an enormous unit of measurement. Most electronic devices use much smaller scales. You will frequently see microfarads, which are 10 to the power of -6 farads, sometimes labeled as MF or F on components. Even smaller are picofarads, which are 10 to the power of -12 farads, occasionally labeled as MMF or PF. A quick tip for your notes. Be careful not to confuse the italicized letter C used for the variable capacitance with the non-italicized C used for the unit coulomb. To understand how a capacitor becomes charged, let us look at a parallel plate capacitor, which consists of two conductive plates of area A separated by a distance would. When we connect these plates to the terminals of a battery, the battery acts as a source of potential difference. This creates an electric field in the connecting wires, forcing electrons to move. Electrons flow onto the plate connected to the negative terminal and away from the plate connected to the positive terminal. This movement continues until the potential difference between the plates exactly matches the voltage of the battery. At this point, the system reaches electrostatic equilibrium, the current stops, and the capacitor holds a stored charge and associated electric energy. Interestingly, even a single conductor can have capacitance. Consider an isolated spherical conductor with A radius denoted as A. We can treat this as a capacitor by imagining the second conductor to be a hollow spherical she-will located at an infinite distance away, where the electric potential, V, is zero. The electric potential at the surface of the sphere is given by K sub E times Q divided by A. By applying our definition, C equals Q divided by the potential difference, we find that the charge Q cancels out. This leaves us with the formula C equals A divided by K sub E, or 4 pi epsilon naught times the radius, A. This derivation highlights a crucial point. Capacitance is determined strictly by the geometry of the conductor in this case, its radius, rather than the amount of charge it currently holds. To summarize our key points, a capacitor is formed by two separated conductors or plates that hold equal and opposite charges, positive Q and negative Q. We define capacitance as the ratio of charge to potential difference, or C equals Q over V. The unit of measurement is the farad, representing 1 coulomb per volt. Most importantly, we have seen that capacitance is a geometric property. While it tells us how much charge can be stored per volt, the value of C itself is determined by the physical arrangement, size, and spacing of the conductors, not by the specific voltage or charge applied to them at any given moment. To wrap up, let us consider two review questions to test your understanding. First, if you take a capacitor and double the potential difference applied to it from V to 2V, what happens to its capacitance C and the stored charge Q? Think about which variable is a fixed property of the device and which one responds to the external voltage. Second, looking at our formula for the isolated sphere, where C equals 4 pi epsilon naught times the radius A, how does the physical size of a conductor influence its ability to store charge at a specific potential? Reflecting on these will help solidify the relationship between physical geometry and electrical capacity.